Good morning, or technically good afternoon, everyone. This is Mr. Steele. I'm here to work through the differentiation review. Particularly for this first year of creating this review, I want to make sure that it's done since I'm going to be gone for surgery. So I want to make sure you have as many resources as possible. As a heads up, I'm going to do this over the course of two different recording sessions just because of the sake of time. Got a couple more events today, in particular a reception for my best friend since he got married last night. So without further ado, I'm going to jump in and just start working through, I think it's the first 15 problems of this review assignment. Nope. The first question we're going to look at is naturally number 1. This one asks us to basically compute a derivative, just a straight up derivative. They're calling it dy dx. We could also call it y prime. And there's just a variety of different terms in there, although all of them do prescribe to the power rule. So we should be able to use the power rule with each one. So before I jump in, an important consideration is that if you're not exactly sure how to begin this problem because they don't all look like powers, it would be to cosmetically alter the function so that it does. So in this case, the 11x cubed can stick around. It's just got a scalar in front of it. But that 6th root of x would be easier for us to work with if we think about it as x to the 1/6 power. That way it matches the x to the n structure that we'd be looking for. Ditto with the next one. We'd have 14x to the negative 3rd power. That way it fits the power rule and scalar rule property, and then minus 2 is just a constant. After that, if we want to find dy dx, also the same thing as asking for y prime, can do that by using the scalar and power rules, as well as obviously the sum or difference rule. So for this first term, I'd do 11 as the scalar times the derivative of x cubed, which is 3x squared. For the next one, I'd have minus 1/6 x to the 1/6 minus 1. And of course, minusing 1 is the same thing as minusing 6 over 6, or subtracting 6 over 6. For the next one, we'll have plus 14 times negative 3 x to the negative 3 minus 1, which is negative 4. Make sure you don't put negative 2, easy mistake. And then the derivative of negative 2 is 0, because it's a constant. From here, although this is fully correct, we could simplify this and write this in a lot better form. So the first term can be 33x squared. The next one will be minus 1/6 x to the negative 5/6. We'll look at that once more in just a second. The next term becomes minus 42x to the negative 4th. And then from here, although again this is perfectly acceptable, we could transform the last two terms just so that they look a little bit more like the terms that we had in our original. For one, we can get rid of a negative exponent on the right term, and in the middle term we can get rid of, or we can transform it into a radical notation. Both though have negative exponents, so a good place to begin would be to transform them out of those negative exponents. For the first one, we'd have 1/6 x to the 5/6, with the x to the 5/6 in the denominator, should have made that clear. And the other one will have minus 42 over x to the 4th. Now again, that's a great final answer. That last term looks great, but if I did want my final answer to have a radical in it, just like the original problem did, the original function did, I could do it as 33x squared minus 6, 6th root of x to the 5th, and then minus 42 over x to the 4th. And of course, since I know some of you like to rationalize, you do not need to rationalize anything here. All you need is to finish the problem with a completely correct answer. And there it is. So again, biggest tip I can remind you of is if you don't see the powers directly there, but you know that they can be represented that way, transform into a power and make your job a whole lot easier. Okay, number two. Number 2 features a little bit of everything in here, throws a little bit of stuff at you. So it asks you to compute the derivative with respect to x of 4 different terms, 2 of which are very simple, because one is linear and one is a constant, but the other 2 of which are going to require some separate rules. Specifically, that first one, with an x squared on the inside of the sign, inside the argument, that's going to require us to use the chain rule. And then second, because of the x times tangent of x, because we've got two different functions being multiplied together that we can't distribute through and simplify that way, we're going to have to use the product rule as well. So there's a couple different rules we're going to need to work with here. I think for simplicity, I'm going to use 2 different colors here to work my way through. Do this, and then we'll do the last ones in purple, just because of traditionals. Okay, so the first and foremost, we want to look at the chain rule problem. I want to start there. We'll start with the chain problem. So we have 5 sine of x squared. And I think that this is a pretty straightforward chain rule problem, one that has kind of a basic application, but at the same time I'm going to do it as formally as possible. So I'm going to first pretend that this is equal to f of x. It's not. It's never defined anywhere as f of x, but for clarity's sake, if we're going to work through the chain rule really fast, I should show it to you that way. So what I'm going to do is I'm going to make a substitution and call something inside of f u, and then I'll let u equal that thing. Remember, our strategy here is to choose u such that it's on the inside and that the resulting derivative on the outside is differentiable by us. We know the derivative rule. So in here I think it's pretty clear that the u we're going to choose is x squared, and what we're left with then is 5 sine of u. From there, if we want the derivative, we're going to have to multiply those two things together. So that'll be 5 sine of u times, in order to get there we need to compute the derivative of each term. So the derivative of 5 sine of u is 5 cosine of u, and the derivative of x squared is of course 2x. From there, not earlier, we need to actually differentiate. From there, we can pretty quickly get our derivative. It's going to be 5 cosine of u times 2x, and then of course we need to back sub for cosine of u, or for u, so that way we get everything in terms. So I'm going to go ahead and multiply the 2x times 5 and get 10x cosine of x squared. So there's going to be the derivative from the first term, which comes from the chain rule. Second, we'll look at the other function here, which is x times tangent of x. So this one's screaming product rule at me, literally because of the multiplication. We said x times tangent of x, so it's all there. So in here, as I go to differentiate, I'm going to be really careful. I'm going to write this as the derivative of the first term times the second term plus the first term times the derivative of the second term. So obviously we've got to know a few rules here, but otherwise it's pretty straightforward. So the derivative of x is 1, so we get 1 tangent of x. And then in the second one we have x times the derivative of tangent of x. Now if you forget the derivative of tangent of x, you could absolutely differentiate it by using the quotient identity, writing it as sine over cosine, and then using the quotient rule. But in fact, I'm more hopeful that you remember the derivative rule and know that it's equal to secant squared, that's the function that gives the slope for tangent, and that just speeds up our process. And here there's not a whole lot else to add, but I can go ahead and just clear that 1 because it's 1 times tangent is tangent. So we get the second part that came from the product rule. Now with all those pieces together, we can finally bring everything together. So we have the first term's derivative, the second term's derivative. So let's go ahead and do that. So our answer here is going to be 10x cosine of x squared. Then it'll be plus tangent of x plus x times secant squared of x. And then finally, we can't forget those last two terms. The derivative of 17x is 17, and the derivative of 1 is 0. So in other words, we are done. So biggest thing here, something you'll notice is first I was looking for potential differentiation rules. I noticed the x squared inside of a trig function that suggested to me the chain rule. And then second, I saw a monomial multiplied times a trig function that also suggested the product rule. So then I went through and I just did each of those rules separately to kind of keep my work organized and make sure I didn't mess up or cross-contaminate stuff. And then finally, I finished the problem off by differentiating the simpler terms and finishing it all out. Okay, that brings us next to question number 3. Question number 3 asks us to compute h prime of 1 for h of t equals 3t squared over t squared, or 3t plus 5, over t squared plus 4. Now in this, what I notice is of course the gigantic fraction bar. I notice that we've got a function over another function, neither one particularly trivial. That suggests to me that the rule we're going to need this time is of course the quotient rule. And we should know and remind ourselves that the derivative of a quotient is not the quotient of their derivatives. We of course have a rule that comes with a nice song as well. So for this thing, before I can start to worry about h prime of 1 and the specific slope at x equals 1, I'm going to go ahead and start by just differentiating the function. Or better yet, even just setting it all up. I think that's even a better way to go through. So looking through here, we've talked about the quotient rule song many times before. Low d high minus high d low, all over low low quotient rule. So that song just kind of helps me remember where all the pieces go. There's other ways to do it. You could turn this into a product rule, chain rule combination by making the denominator to the -1 power. But again, I like being able to have something kind of fun way to remember it and actually just apply it pretty quickly. So to start with the song, low of course being the denominator and high being the numerator. Low d high, we'll differentiate it in a second, minus high d low, it moves a lot slower than you'd expect, all over, gotta get this line straight, low, low, quotient rule. So there's our stuff. Now all that's left is evaluating some derivatives, distributing some stuff in, and simplifying it as far as we want to, as well as, of course, plugging in 1 at the very end. So as far as ingredients here, the derivative of 3t plus 5 is 3. So I'm going to write this as 3 quantity t squared plus 4. And then for the second one, the derivative of t squared plus 4 is just 2t. So we'll have 2t times 3t plus 5. All of that was a terrible line. So we're having fraction bar problems here. All of this is t squared plus 4 squared. Okay, so looking at all those ingredients, I now need to distribute and make sure that we distribute that negative sign. That's where a lot of mistakes happen here. So we're going to get 3t squared plus 4. Nope, just kidding. Look at that, I almost made the mistake. Plus 12, 3 times 4. The next one, I'm going to get minus 6t squared minus 10t all over that denominator. And although it's not maybe perfect at this point, you'll notice that I haven't distributed out the denominator because, again, we're going to have to plug in a number anyway, so there's no reason to make it worse than it already is. We'll just leave it as simple as we can. Oops. Okay, from here, this can simplify just a little bit. It's not going to be the most elegant looking numerator, but we'll live. So we get this guy. So there is our derivative. I would in fact say that this is a mighty fine looking h prime of t. But remember, our question wasn't asking us specifically for h prime of t. It specifically wanted us to find h prime of 1. So for us to finish this guy off, we want the slope of the function h at x equals 1, or the slope of the tangent line. So from here we can plug in 1. We'll get negative 3 minus 10 plus 12. And then down below, we'll have 1 squared plus 4 squared. So as far as ingredients, we get negative 13 plus 12 over 5 squared. It's going to be negative 1 over 25. Voila. So we have our stuff. We'll use the quotient rule by recognizing the presence of function divided by another function. After that, we'll use the quotient rule song to low D high our way through the problem. And once we finished it up, we're able to plug in 1 and simplify it to get the specific slope. So pretty straightforward problem, very basic quotient rule, but a good one to practice with, especially with signs and terms to multiply out. That next brings us to question number 4. And question number 4 looks pretty intimidating if you focus on like the question mark first. It asks us what is the fourth derivative of y with respect to x, also known as d to the fourth of y, or d quadrad, I don't know, d quadrad, yeah, who knows. That wants the fourth derivative. And that would take a long time and a lot of work to get there. But notice, we're starting with the second derivative. So if you think about that, what it's going to take is we're going to start with y double prime, then we'll differentiate once to get to y triple prime, and then after differentiating one more time, we'll end up at the fourth order derivative of y. So this actually isn't going to be as bad as it looks. We just have to make sure that we carry things through, and naturally I didn't make it easy for you with one of the terms. So now, before we jump in and start differentiating to go first from second derivative to the third derivative, let me point out that this isn't going to be so simple. This has 5 sine of 3x, and because of that 3x on the inside, this function actually requires the chain rule. Or at the very least, this first term requires the chain rule. So we must take care of that and make sure that we're careful as we move our way through. So a good place to begin might be to just kind of think our way through. And in fact, I'm going to recommend this chain rule just be to thinking. You can obviously write more out if you want to. I just think this would be a good place to practice it. If you take the derivative of sine of 3x, let's think about what you're going to have to get. You're going to naturally get cosine of 3x, of course. But then ask yourself what the derivative of the inside is. And your mind will naturally say 3. And since there's a 3 there, we would have to multiply this expression by 3. If we then take the derivative one more time, we're still going to have to do the chain rule. So another 3 will come out. Let's do this right. Another 3 will come out in this case. So we'll still have the derivative of cosine is negative sine of 3x. But since we're multiplying by a 3 again, and we started with 1 there already, we're actually going to end up with negative 9 sine of 3x. And that didn't even take into account the scalar that's over there. So something to keep in mind, we don't necessarily have to keep going forward. We can think our way through and save ourselves from writing the f of u and u prime stuff over on the side. So in this particular case, the first place I'm going to begin is I'm going to try to compute the third derivative of y with respect to x. So in looking at the pieces here, we just talked about it. The derivative sine of 3x is going to be 3 cosine of 3x, with that 3 coming from the chain rule. And then keep in mind there's a scalar of 5 out in front. So definitely need to have that there as well. Next, when we take the derivative of 11x to the fourth, we'll have the 11. And then the derivative of x to the fourth is 4x to the 4 minus 1, or third power. So that means our third derivative, which isn't what we wanted, but something we need in order to get through to the fourth derivative, is going to be 15 cosine of 3x plus 44x to the third. So that gets us halfway there. In a sense, we just reached here. We want to go to the promised land, which we're calling the fourth derivative, though. To wrap that up and make sure we get the rest of the way there, we need to differentiate this guy once, the one that we just calculated. So to get to that, I keep writing the wrong power. So to get there, we need to think about again what the chain rule does. First, of course, we have that 15 scalar out in front. Then as far as the chain rule, the derivative of cosine of 3x is negative sine of 3x times the derivative of the inside. And the derivative of the inside is once again 3. So that 3 once again comes from the chain rule. And again, with scalars are really simple chain rule things. I mean, you're welcome to write it out every single time like we did a couple pages ago, but you don't have to. If you're comfortable with it, which I hope you are, you can move through it a little quicker. Okay, we have the chain rule taken care of there. We have our first term. The derivative of the next one is 44 times 3x squared, because the derivative of x cubed is 3x squared. And then from there, if we start to simplify these pieces into a good solid final answer, we'll get negative 45 sine of 3x. And then over here, we do have to do 44 times 3. As a heads up, I can do that in my head. It's going to end up being 132. A couple different ways to get there, but just so you can kind of see what I do. I basically think of 44 times 3. This isn't related to calculus. This is just kind of like fun math stuff. I think of that as 3 times 40 plus 4. I know that's 120 and 12. And that quickly gets me to 132. So 132x to the second. And there are our two derivatives we needed. The third derivative to get to the fourth, to begin the possibility of getting to the fourth, and the literal fourth derivative, which represents our answer here. And just to boot, you got a little bit of mental math strategy for free. So there is question number 4, answered, signed, sealed, delivered. It's yours. Question number 5 brings us to another kind of vocabulary piece. It's something you've done many times before. It says for the interval -1 to 5, inclusive, what is the average rate of change of f of x equals 2 to the x plus 14? So we're using that vocabulary of average rate of change. Now that was probably a new terminology for something you'd used many times before. We think of the average rate of change as f of b minus f of a over b minus a. And again, that word average does not mean the traditional add them up, divide by 2, or however many are there. We're talking about this average rate of change difference quotient over here. Another word, though, just to remind you, is this is just another fancy way of describing y2 minus y1 over x2 minus x1, the traditional slope difference quotient. So in here, though, in our particular case, for us to evaluate the average rate of change, we're going to be using f of x over here and the interval from -1 to 5. So our difference quotient is going to be f of 5 minus f of -1. All over 5 minus a -1. So thinking things through, we're going to end up with a denominator of 6, of course, because that's 5 minus a -1, or 5 plus 1. F of 5 is going to be 2 to the 5th plus 14. We'll deal with that in a second. And f of -1 is going to be 2 to the -1 plus 14. So again, totally correct answer, actually. Like, I could see an argument for stopping right there, but that's not a luxury I have. So I shall continue. So first of all, 2 to the 5th is 32. It's 2 to the 3rd times 2 to the 2nd. Lots of different ways to get there. So 32 plus 14 is 46. On the next one, actually, let's do this. I just realized something. Do you see how there's a 14 there and a 14 there? They're going to actually simplify away. So I'm going to write it like this. 32 plus 14 minus whatever 2 to the 1/2 or minus 1 power is, minus 14. And as far as the 2 to negative 1, we can use the negative exponent rule and write it as 1 over 2 to the first, or 1/2. And then once again, all of this is over 6. From here, we can zero out the 14s. We get 32 minus 1/2, which is 31.5. But I guess for simplicity, we might write this as 64 over 2 minus 1 over 2, all divided by 6. And simplifying it, we'll get 63 over 2 divided by 6, or 63 over 12. Now that is a perfectly sensible answer, but of course 12 and 63 share a common factor. They each have a 3 in them. So our numerator is 3 times 21. Our denominator is 3 times 4. That means that the most simplified answer for us is going to be 21 over 4. Or 5.25, 5 1/4, lots of different ways to get there. In any event though, anytime you write the average rate of change, it's highly recommended that you first write the difference quotient by itself. I say this because as an AP reader, I've, I think twice in the last 3 years, graded problems where you get a point just for having the correctly stated difference quotient. And well, yeah, of course you should be able to plug in. If you make a mistake over here, if you don't have that, you don't get that point. So you want to bank that point as early as possible. But that is question number 5, the average rate of change basic question. Okay, the next question, 6. Like I tried to mix in a little bit of problem-solving kind of stuff to kind of keep you on your toes and keep you interpreting and using the derivative to answer some different style questions. I think this one fits in a little bit. For question number 6, it asks us for which x values is the tangent line to x cubed minus 5/2 x squared plus 4 parallel to the line y equals 2x plus 13. Well, I think the most important word in there to start with, since it's necessary to have you access the solution here at all, is that if two lines are parallel, that implies something about the two things. Hopefully what you remember is it implies that they have the same slope. In other words, if two lines are parallel, their slopes are the same, meaning that they'll never intersect because they'll always be running alongside each other, never deviating from that path. So if that's true, we want these two lines to have the same slope. So let's look at the ingredients here. We have two different things to look at. Wow, I just cut myself on some paintings. Okay. X cubed minus 5/2 x squared plus 4. So that's one relationship we have to deal with. And the other one is the tangent line 2x plus 13. Or just a line. So first thing I'll note is that y prime is equal to 2 for that tangent line. So what we're really looking to figure out is when does that function have slope 2? Because it's at that spot that it'll be parallel to that other line, since that other line has slope 2 everywhere. So in our case, it would be helpful to start by figuring out what the derivative is. I see 3x squared minus 5x, so it looks pretty promising. And in order for us to solve this, we need to end up with those two equations brought together. So we want to know, when does 3x squared minus 5x equal 2? And there should be two potential answers here, it looks like. So in looking, so 3x squared minus 5x, I can subtract the 2 over. So I just subtracted it from both sides, maintains balance and everything. At this point, we're looking for what two numbers multiply to -6 and add up to -5. So if you're a diamond guy, you could probably do that. There's lots of different ways you could do this. In my mind, though, multiplying to -6, adding up to -5, I hear x minus 6 and x plus 1. But of course, you would argue that this is wrong because of the presence of that 3. Absolutely right. What I'm going to use is what I was taught to call the butts up method by a student I tutored years ago. So what I'm going to do is I'm going to divide both of those ending pieces by 3. When I do, I get x minus 2 for the first one. For the second one, because of the presence of that 3 down there, it doesn't simplify. So I'm going to bring it up and make it 3x plus 1. It's bringing the butt up because it's low, you bring it up. So at this point, I might just check 3x squared plus x minus 6x, yep, minus 2. Looks to me like we got those things correct. So at this point, we wanted to solve this equation, which amounts to figuring out when this is equal to 0. And in looking at our ingredients here, it looks like that's going to happen at x equals 2 and x equals -1/3. So it looks like there are two spots where the slope matches up to that tangent, to that line 2x plus 13. So again, if we wanted to, we could absolutely check this. In fact, maybe we will just for the sake of completion. See if we got Desmos. Okay. So if we look at Desmos, I know we had y equals 2x plus 13, I want to say. So there's our line. Next we had x cubed minus 5 halves. Okay, so our question is, do we have slopes at the appropriate times? Oh, one way I can do this, I love the fact that Desmos lets me do this. I'm going to check the two values that we found. So first, let's see what f prime of x, or f prime of 2 is equal to. It says f prime of 2 is, was it 2 or negative 2? Sorry. It looks like it should be 2. So we're supposed to get a slope of 2. And oh, look at that, we did. We got a slope of 2, sorry. Having these non-glasses on makes this kind of hard. And then I think the other one was negative 1/3. And in fact it was. So it means the tangent line over on those graphs was 2 right at that spot. And it looks like we did pretty well there. So if we wanted to construct this really fast, y minus f of c equals f prime of c. So I was constructing a really quick tangent line. If we let c equal 2, oh sorry, I hit 3. If we let c equals 2, you can see that these two guys do in fact look like they're pretty parallel. At least it looks that way to me. And then same thing if we let c equal negative 1/3. You can see that those are parallel as well. So doing nice stuff. Things are looking pretty good so far. Looks like we're, looks like we're in really good shape. We got question number 6 answered as well. So key thing though, again, just because I think it's always nice to remind you what's most important here, the relationship you had to know was that parallel means that two things have the same slope. So in other words, the tangent line and the curve would have to have the same slope, or the tangent line and the line would have to have the same slope of 2, and that gave us an equation we could construct and solve. Okay, with that said, that brings us next to question number 7. Question number 7 is just looks like some sort of relic from the limits unit. It just has evaluate, basically just asks for the value of the limit as x approaches 7 of this quotient up here. So in here though, if you'll recall, we defined derivatives in the very beginning using one of two definitions. Those two definitions were the limit as h goes to 0 of f of x plus h minus f of x all over h, with h being some small horizontal distance, and the second one being the limit as x approaches c of f of x minus f of c all over x minus c. So now given those two definitions, each one defined a particular derivative or a particular part of the derivative. So the first one provides us the literal derivative function f prime of x. So it gives us the derivative at any x value on the graph of f, assuming things are differentiable. The second one also gives us the derivative, but not the whole derivative. It gives us the derivative at a particular point x equals c. So given that piece, like basically we had two different ways to approach it depending on what we were asked for. Now, in order to evaluate one of these limits using differentiation and derivative rules, the important place to begin is to identify which one of these two definitions, or limit definitions of the derivative, actually matches. And I think it's pretty obvious here from looking at the denominator structure, as well as the fact that our limit is as x approaches 7, not as a tiny horizontal distance approaches 0. So that tells me we're not going to use the first one, we're going to use the second one. So this is the one we're looking for. So in other words, this expression is equal to some function's derivative f prime. And in fact, if we wanted to, we could even say that that's equal to f prime of a particular x value. And I think you can see what c's value would be for this limit. It's going to be 7. So we're looking to find the value of f prime of 7 for some function f. Now once here, what you can do to kind of match these pieces up is you can imagine you're just kind of matching stuff. Actually, I'll do this. I'll leave it there. I cut it over here. You're trying to make these things fit together and trying to see which part goes where. So as I look at the actual definition, I see f of x, the function being differentiated, is what's at the very beginning and it's in terms of x. So following that pattern and seeking structure here, I'll recognize that our function f of x in this case, if we're going to so call it that, is equal to tangent of 2x. So tangent of 2x is what we want. Now, in order for us to finish this and evaluate the limit, we're supposed to find f prime of 7. Well, the of 7 part's not bad. Our difficulty is going to come from the f prime. So in order to find f prime of x, we need to pull out any possible derivative rule we can. In our case here, with tangent of 2x requires the chain rule. So in other words, in order for us to find it, we're going to need to actually use the chain rule first. Now this is another one of those with a scalar inside, so I would like to think that you could actually work your way through it, but just, I'll try to alternate how often I do this. We can also do this using the decomposition method here. We can break this down into an outside function and the inside substituted part, and then differentiate each piece to satisfy the chain rule as well. So in our case, if we let the inside be 2x, which seems like a pretty good choice because it's literally inside the tangent, means our outside is tangent of u. If we take the derivative of each component, we're going to have secant squared of u, and the derivative of u is just 2. So our derivative f prime of x, the one we're looking for, is going to be 2 secant squared of u. But recall, we said at the very beginning of our setup here that u was equal to 2x. So this will actually be 2 secant squared of 2x, and even over here we'll have 2 secant squared of 2x. So that is our approach to getting the literal derivative f prime of x, like figuring out what function's being differentiated in this guy and then differentiating it. But remember, we didn't want f prime of x. Oops, we didn't want f prime of x. We wanted f prime of 7. So to finish this puppy off, we're going to plug in 7. And of course, there's not much we can do here because we're not getting nice angles, but there is our answer. 2 secant squared of 14. And again, what that represents is the slope. In fact, let's write this once just so we can always throw it back. This is the slope of the function tangent of 2x at x equals 7. So we just found a particular slope, and voila, we have it. So and again, I think your key here is knowing these two limit definitions, like knowing those structures, almost like they're limit identities, being able to recognize them by comparing it to something you have versus something that you know, the structure you know, and then finally assembling all the pieces, computing the correct derivative, and then plugging in the correct value. So strong question, this is a great one. In fact, I could swear I remember doing a question very similar to this one on a quiz from Mr. Friedrich's class, but it's been a while. So there you go, there is number 7. For number 8, we bring in our first piecewise function here. And again, I hope you've made some peace with piecewise functions. For the moment, we are to consider that piecewise function, and first for part A, compute the derivative, and then second in part B, it asks us to determine the 2 places where p of x is non-differentiable. And I can see one just from looking at the original function, but we'll play along for the moment. So first and foremost, if we want to compute the derivative of this thing, it might be useful right off the bat to just remind you that 24 over x plus 3 is the same thing as 24x plus 3 to the negative 1 power. In which case then when I write p prime of x in this way, hopefully you're comfortable with where it came from. Bring down the power, we'll get negative 24 x plus 3 to the negative 2. So in our function here, we'll have negative 24 over x plus 3 squared. That'll be true for x values less than 1. Again, we don't know exactly what's happening at 1, so I'm going to play it a little more carefully here, although I'm not going to judge you for that when you actually take a test or quiz on this topic. And then second, for the second function, the bottom half or the right half, we have x squared, whose derivative is 2x, and we have 5x, whose derivative is 5. So for the moment, there's our derivative. We could check to see if it's differentiable at that point, but we're about to do that anyway. So first and foremost, there is the derivative of that piecewise function. All you're literally doing is differentiating twice. Okay, from there, for part B, actually I'll change the color here. For part B, as we look at part B, we're supposed to tell where p is non-differentiable, and we want to find the 2 values. The first things I want to remind you are the types of non-differentiability we have. The first one is the simplest. If there is a discontinuity on the graph of that function, then it is non-differentiable there. If f is differentiable, it must be continuous. If f is not continuous, then f is not differentiable. So discontinuity is the first one. The second one is what's called a sharp turn. Like there were other terms that we mentioned for it. Corner, cusp, pointy point. Talked about the anecdote about the word doink. But all of those things are all different ways to describe the same thing, but sharp turn is the term I'm looking for. And then finally the last one is what we call a vertical tangent line. And these are pretty much at this moment endemic to cube root functions and odd root functions, but we will run into more of them later when we deal with circles, ellipses, hyperbolas, all that good stuff. So for the moment, those are the three that we're looking at. So we need to figure out which one's which. Well, now the first thing I'm going to point out is that there is definitely a vertical asymptote at x equals -3. And I saw that from the very beginning because of this denominator of x plus 3, but more than that, because -3 is less than 1. So right there I can go ahead and point one out that there's a vertical asymptote, and that is a discontinuity. So although I'd totally just accept VA at x equals -3 for that first answer, I think it's a good starting spot just to establish that there's a discontinuity there. So the function the function p is non-differentiable. Unfortunately though, it says both, so there's one more discontinuity for us to hit. And in looking at this, it's sometimes hard to tell. Is this second discontinuity going to be a literal discontinuity, or is it going to be a sharp turn or a vertical tangent? Well, a vertical tangent isn't going to be there just because of the fact there's not going to be a vertical tangent at the boundary, because of the fact that there's no cube root in here, and we've just got a literal asymptote and an actual function. So we don't have to worry about the vertical tangent line. Again, vertical tangents are typically odd roots. So basically that's not going to be our option on this one. It's got to be a discontinuity or a sharp turn. Now, to actually check and see which one is which, we can make that call by checking two things. First, we want to see if the function is continuous at x equals 1. That's the first place we'll look at. So for here, although again the continuity definition requires 3 steps, f of c exists, limit as x approaches c of f of x exists, and those two things being equal, we're going to settle for checking if the left hand and right hand limits are equal one another, specifically at x equals 1. So looking up there, we'll have 24 over 1 plus 3, and our question is, will that be equal to the right hand limit, which will be 1 squared plus 5 times 1. So we're looking to see that's 24 over 4 is 6, 1 plus 5 is 6. So we just saw as those two things are there. That means that our function p is continuous at x equals 1. So that's really nice. That means that we don't have a discontinuity there. So that means there must be a sharp turn here. The question is, though, how can we tell? And to do that, let me remind you that in reality what we were checking was, is p continuous at x equals 1? The second one, we're going to check if its derivative, p prime of x, is continuous at x equals 1. And because of the picture video thingy, I got to move that over. Sorry. So we're going to check if the derivative is continuous at x equals 1. So in looking at all of our ingredients here, we've got a lot of stuff to deal with. We're just going to plug in 1 to our derivative, which conveniently you had already found here. So if we look at the left hand and right hand limits, for the derivative, of course, we're going to get negative 24 over 1 plus 3 squared. And then we're going to compare that to 2 plus 5. So on the one hand, we get 7. On the other hand, we get negative 24 over 16. And I'm very certain that those two are not the same. So what that tells us, because the slopes were different, but the 2 points came together at the correct spot, in other words, if the function was continuous at x equals 1, that means we have a sharp turn at x equals 1. And we now have our second non-differentiable point. So everything's satisfied. So as far as pieces here, like the first thing to note is differentiating a piecewise function, just take the derivative of each two parts. I'm less worried about the or equal to side. Although technically you can tell once you've figured out if the function is differentiable or not. After that, we were asked about the types and where the different non-differentiable points were. In order to do that, the first thing is I looked for any blatant discontinuities. Like for instance, I saw that vertical asymptote at x equals negative 3. It was in the correct boundary or side of the function as well. And then second, I looked to see if the boundaries, any boundaries we had, were both continuous and differentiable, meaning was p continuous at the point and was p prime continuous at that point. It turned out in this case p was continuous at 1, but p prime is not, meaning that there's a sharp turn such that the slopes came together in a non-equal way. In fact, this one has one that's negative. Let's see if I can do this right. One that's positive. I can't tell for you guys. So there we go. That is question number 8. So that brings us next to question number 9. Question number 9 has just been fixed. So question number 9 asks you to write the equation of the tangent line to y equals this function that has some powers to raise to a power. Some sort of behavior inside the function too, so we'll keep that in mind in just a second. And it says it wants it at y equals -3. So it's just a general rule, since I think this is our first actual tangent line. We're going to have y minus y1 equals mx minus x1 as the equation of our line. We want to keep that structure just because it minimizes the likelihood of a mistake trying to simplify or combine like terms or anything. So we'll aim to get it there. In order to get there, though, that means that we do need 3 different pieces. We need x1 and y1, and we need the slope at that point. So in order to get things started, a good place to begin would be to find the point of tangency. It's usually a good thing to get your inertia moving. So in this case, that's going to be whatever y is equal to when x equals -3. So for our purposes, that's going to be 1/16 -3 to the 4th minus 79, all to the 5th as our y value. And in looking here, this looks pretty bad, but -3 to the 4th is 81, minus 79 is 2, so 2 to the 5th. So we have 1/16 times 2 to the 5th. And if you recall, 2 to the 5th is just 32. So we literally have -3 comma 32 over 16, which is -3 comma 2. So actually our x1 and y1s are actually pretty clean values to find. So we're in great shape so far. The harder part is probably going to be y prime. So to get to y prime, we're going to need to take the derivative. And in this case, because of the presence of that x to the 4th minus 79 on the inside, this requires us to use the actual chain rule. And now I will point out that if you are just vehemently opposed to the chain rule, you could just not use the chain rule if instead you multiplied out this binomial to by itself 5 times. So good luck with that. We're probably going to just use the chain rule. So in here, looking at our ingredients, we're going to have first y as a function of u, and then we'll figure out what u is equal to on the inside. For the inside, I think it's probably the thing in the parentheses. That's a pretty standard place to look. So I'm going to choose x to the 4th minus 79. That means the outside is 1/16 u to the 5th. Taking the derivative, you don't have very far to go. So this is going to be 5/16 u to the 4th. U prime is going to be 4x to the 3rd. And if we multiply those two together, as we are wont to do, we're going to end up with 5 over 16 times 4x cubed times u, which is x to the 4th minus 79 to the 4th power. And cleaning things up just a little bit more, we're going to get 5/4 x cubed, quantity x to the 4th minus 79 to the 4th. So hey, that's really nice. Like if that's our y prime, and I'm going to be that guy that... Oh, are you kidding me? The computer doesn't want me to be able to save a second's worth of time. Go figure. Well, I'm going to beat the computer at it. Okay, so given that this is our derivative, remember we can't just shove that in the tangent line because we're looking for the derivative specifically at the ordered pair we were interested in. In our case, that means we need to make sure we find the slope at specifically x equals -3. So in our case, y prime of -3 is going to be 5/4 times -3 to the 3rd. This will be -3 to the 4th once again, minus 79, but this time all to the 4th power. And then we have to simplify as much of this as we can. So we'll see how clean this turns out. I'm not sure it will. This is 5/4. This is -27. Make sure you don't put -9. It's a common mistake. In this case, we'll get 2 to the 4th power. In looking at all these ingredients then, 2 to the 4th is 16. So we have 5 times 16 over 4 times -27. And pulling out the last couple ingredients here, the 4 and the 16 can divide out. We'll be left with 5 times 4, which is 20, times -27. And that's going to be -540. So that came out okay. A little bit big, but it was reasonable. And then for us to finish off the problem, all we have to do is put all the ingredients in the right spot. We'll have y minus 2 equals -540. And then quantity, sorry, just going to move this up a little bit. Quantity x minus a -3. So there is our tangent line equation. And again, the path we took to get there, followed up coming out of that final work right there. So again, when we're dealing with tangent lines, of course you want to find the point itself, x and y, usually by plugging x into the function. And then you want to find the slope. In this case, we did have to use the chain rule, so it took a little bit more to get there. But not a super difficult problem to attack. A pretty standard chain rule problem. That next brings us to question number 10. Question number 10 asks us to find all points x, y on the graph of f of x equals that parabola for which dy dx equals 5. So in this case, they're telling us the slope and the function, and they want us to find the point. It's almost like without sounding too much like a MasterChef candidate or competitor, it's like we're creating a deconstructed tangent line problem, and we're trying to focus our attention on the cream fraiche that's going on one side. Like, I don't know. Just watched the most recent episode this morning, so that's probably why it's in my head. Okay, so in here, if we want to talk about dy dx and figure out when it's equal to 5 specifically, what we're going to need to do is figure out what dy dx is. So let's start there. If y equals f of x, then that's going to mean that dy dx is equal to f prime of x. So what we need is the derivative of f of x. Well, this isn't a particularly difficult one. Our derivative is one that I would expect you should be able to do. It's going to be 2/7 x minus 5. And so we just found that that is dy dx. But we want to figure out when dy dx is equal to 5. So let's go ahead and put that in. So looking at all of our ingredients here, we put in 5. We just have our equation to solve. I'm going to add 3 to both sides then. That means 2/7 x is equal to 8. In this case, we're going to multiply both sides by 7 over 2. So that's going to give us x is equal to 56 over 2, also known as 28. So we've got our x value. We know our answer is going to be the point 28 comma something. Our job now is to figure out what is that something. So from there, it wants the y value. Well, since we said y is equal to f of x, that just means that we want to calculate out what f of 28 is. So in looking at our ingredients here, we've got 1/7 of 28 squared minus 3 times 28. Now there's lots of strategies we could take here. I'm looking at a couple. I want to simplify this, and of course you could just go right at it. I mean, you'd be able to figure this out. It's going to come out to be a whole number. But I'm going to be kind of clever here because I don't want to have to multiply anything humongous out, and I don't want to have to reach for a calculator and cheat the fact that it says no calculator up there. So what I'm going to do is I'm actually going to pull out a GCF of 28. This is going to become 28 times 1/7 of 28 minus 3. And looking at all that, we're going to get 28. Look at this. Is that right? 28. 1/7 of 28 is 4 minus 3, which means this whole thing is equal to 28 times 1, which is 28. So bizarrely enough, in a problem that I just completely made up off the top of my head earlier this morning over breakfast, or actually it was before the wedding yesterday, before I practiced my reading, it ends up being that the ordered pair 28, 28 is actually the point where the slope happens to be 5. You can't make this stuff up, except I did, and somehow it turned out really, really nice. And now I fear all my good luck has been wasted on writing question number 10 on the Differentiation Review 2019. Oh well. That's number 10. So again, most important thing, find the derivative, set it to 5, work your way through. Pretty standard kind of question, but asked in a different way. Next, that brings us to question number 11. And we've already talked a little bit about evaluating the limits of a difference quotient. In this particular case, though, we've got the different structure. We've got one involving an h. So rather than listing both of them out there, I'm just going to think about which one looks like that. And we already said the traditional definition, limit definition, is the limit as h goes to 0 of f of x plus h minus f of x all over h. So in looking at these ingredients here for a second, what we want to do is kind of match up all the different pieces. So in a sense, as I did on the last one, I want you to look at this limit and try to seek out all the structure. Try to match up the pieces and figure out what we're looking at and how it compares to what we were given. So there's our stuff. So now with that said, as I look, I know that this expression is equal to f prime of x. And looking in here, this is going to be equal to f prime of x as well, because it literally has x's in it. So we're actually computing the derivative of some function here. So if this is equal to f prime of x, the reason that's so helpful then, oh, are you kidding? Oh, whatever. Since that's so helpful is we need to figure out what f of x is. And in our actual structure here, we say that f of x is the thing being subtracted in the numerator. Up here, that thing being subtracted in the numerator is cosecant of x. That means that the function whose derivative is being represented up here is cosecant of x. And that means all we need to know is the derivative of cosecant of x. Now some of you go, oh crap, I don't know the cosecant of x's derivative. Oh shoot, what do I do? Well, you should learn it. You should probably put it on flashcards if you're not sure, or find some way to quickly derive it. And by derive, I don't mean differentiate the function. I mean you could actually derive the derivative rule itself by using the quotient rule. So I guess for the sake of time, we could. I mean, it's not the end of the world. I've got a little more time before I get ready for that reception party. So in here, let me just remind you, cosecant of x, whose derivative we're trying to compute, is equal to 1 over sine of x. So in our case, what we want is to differentiate 1 over sine of x. We can do that using the quotient rule. So low is sine, high is 1. So low d high, we'll do that in a second, minus high d low, we'll just mark this in a second, all over low. Up there, derivative of 1 is 0, so that whole first term goes to 0. Derivative of sine is cosine, so we end up with negative cosine of x, all over sine of x squared. As far as our ingredients then, if we separate this out into negative cosine of x over sine of x times 1 over sine of x, we can get the expression we're looking for. Negative cotangent of x times cosecant of x, which is pretty much which isn't exactly the standard way of writing it. Typically people write this derivative as the reverse, negative cosecant of x, cotangent of x. However they write it though, that is the answer and what is represented by that particular limit. That is just the traditional definition of the derivative. Is even in terms of x, so pretty straightforward, but it was an opportunity to prove you know the derivative of cosecant, which if you don't, you have to. So go do that. Okay. Next, that moves us to question number 12. So question number 12 is a new one, and I haven't done the work here on this, so I'm going to attempt this just like I would looking at it with fresh eyes. So it says that g of x is an even function with g of 4 equal to 8 and g prime of 4 equal to negative 2/3. It wants us then to find the tangent line to g of x at x equals negative 4. So first of all, it's worth reminding you what an even function is. This is something we don't use all the time, but it's something that you should know. Recall that an even function f of x is a function for which f of negative x is equal to f of x. Visually speaking, what that means is that there's a particular type of symmetry. The symmetry in this case is that whatever happens on the right side is exactly mirrored on the left side. That's literally what makes it even. As in, if we choose a point on each side, let's say this is 5 comma f of 5. Oops. Since the x value or the y value has to be the same, the y values have to be the same on opposite sides. That means this point over here would be negative 5 comma f of 5. They'd have the same y value. Now the reason I bring this up and draw a picture is I think you might be able to anticipate this answer and get it correct without actually having to do any differentiation or any fancy thinking. Here's my thought. I don't know why I've got the southern accent going. Who knows? Here's my thought. As I look, I notice that these two things have to be complete reflections of one another. But on the right side of my little picture I drew, I have a positive slope, whereas on the left side, at that place, I have a negative slope. So if I had to guess, and this is just a guess, we're not confirming this, I'm just guessing it straight off the bat, I would guess that our slope at negative 4, which is going to end up being the crux of this problem, is going to be equal to the opposite sign of whatever we started with. So my thought is that we're going to find out that the slope is 2/3 over there. That's just my guess though. The rest of the stuff we can work with. So just know that's kind of my thought. This is my strange fish cloud-shaped brain. So this is all a guess. So now let's go into the actual work here. So first and foremost, we're talking about g of x at negative 4. So the first thing we can do is figure out what is g of negative 4, because that's going to end up being our y1, or y sub 1. So in there we said that with an even function, since g is even, that means that g of negative 4 is equal to g of 4. So in our case, since g of 4 is 8, that means g of negative 4 is 8. So for our tangent line, we're going to be at the point negative 4, comma 8. So same y value, opposite x value. That is required by the evenness of this function. So there's our first move. Now our second move, I'm going to be clever here. What it tells me up at the beginning is that f of negative x, so in this case I'm going to say g of negative x, is equal to g of x. So what I'm going to do to this relationship is I'm going to take its derivative with respect to x, and I'm going to see what it tells me about the actual slopes. So working through this pretty quickly, on the right side we're just going to get g prime of x, and that'll be helpful. We'll be able to plug in 4 eventually to figure out what this, we know that slope at 4. On the left side though, because of that negative sign, we have to use the chain rule. And the derivative of the inside in this case, everybody, is negative 1. Exactly. The derivative of the inside is negative 1. That means our derivative there using the chain rule is going to be negative 1 times g prime of negative x. So in looking at all of these ingredients, like this isn't easy, like this is complicated, kind of weird, but basically remember what we're looking for here is we want to figure out what's happening at x equals negative 4. So what I'm going to do next is I'm going to evaluate this entire equation at x equals 4. When I do, I get negative g prime of negative 4 is equal to g prime of 4. Now from there, we don't know what g prime 4 negative 4 is, so we still have negative g prime of negative 4. But on the right side, we know g prime of 4 is equal to negative 2/3. So we now have negative of that number that we want is equal to negative 2/3. From there, you could just multiply or divide both sides by negative 1, and you'll get that g prime of negative 4 is equal to 2/3. So basically, as we guessed at the very beginning, based on this kind of image we drew, it looks like the slope on that other side is actually equal to the opposite sine slope of what we had before. So given that, since g prime of negative 4 is now 2/3, that gives us enough ammunition to figure out what the equation of our tangent line is. We have our ordered pair, we have our slope. That means our tangent line in this case is going to be y minus 8 equals positive 2/3 x minus a negative 4. So interesting thing, I mean at this point you can take this as canon. We now have established that the derivative of an even function on the opposite side has the opposite sign. It's got to be a reflection, which means that it's got to actually flip. We also saw how the chain rule could be used to verify that relationship. And in this case, we're able to find our tangent line, and it behaves exactly the way we'd want it to. Wish I could show you an example that looks this way, but I think the picture and everything here has done a really good job of it. So this might be one that you look at a couple times, but I think this is a good question. I think it's a good opportunity to demonstrate your knowledge of evenness and oddness, as well as be comfortable working with them in unique ways. From there, this brings us to question number 13. 13 tells us that there's a tangent line to some 6th power function, kx to the 6th plus 10x plus 3, presumably for some real value k. I should probably say that in the question, my bad. And it says that that tangent line to that graph at x equals 1 is perpendicular to the line 5/2 x plus 10. And then it wants us to find the value of k. So once again, using some slope relationships that you've used before, recall if two lines are perpendicular, what that tells us is that there's a particular relationship between their slope. It means the slopes are negative reciprocals. And geez, it takes a long time to write all these words out. This is a crunchy statement, I'll tell you that much. So in other words, if one slope is m, the other slope is negative 1 over m. So basically that's kind of our good place to start. So a couple things that we can do in order to jump in. So the first thing I'm going to take advantage of is it says that the thing that we want is going to be perpendicular to the line y equals 5/2 x. Well, in other words, what that tells us is the slope that we're looking for is going to be equal to negative 2/5, because that is literally negative 1 divided by 5/2. So basically, the first thing we know is that whatever we get, we're going to need to make sure that the slope that we get from the original function is equal to negative 2/5 at x equals 1. The second thing that we can look at is we can look at the actual function here. So there's our parabola that we're talking about. Or not parabola, there's our bowl, I guess you could call it, our even degree function. So in here, if y equals kx to the 6th plus 10x plus 3, that implies that y prime is equal to 6k x to the 5th plus 10. Now we want the slope specifically at x equals 1, so y prime of 1 is going to be equal to 6k times 1 to the 5th plus 10, which is equal to 6k plus 10. So given that, we need 6k plus 10 to be equal to negative 2/5. because in that way, whatever our slope is, let's see if I say this correctly, our slope is, it's going to be perpendicular to 5/2 x plus 10. So in here, solving some of the ingredients, I'm going to write this as 6k equals negative 2/5 minus 10, but keep in mind 10 is the same thing as 50 over 5. So basically at that point, we get negative 52 divided by 5. And since 6k equals negative 52 over 5, let's make sure I do this right, 6k equals negative 52 over 5. We can divide both sides by 6, which is the same thing as multiplying by 1/6. When we do, we'll get k is equal to whatever this is. I can divide out the 2's. I'll get a 3 and a 26 on top. We're going to get that k has to be negative 26 over 15. And if k is that, then supposedly the two lines will be perpendicular. So and again, if I had a little more time before I have to leave, I would go ahead and graph this on Desmos and show it to you, but the steps that were followed here were accurate. Start with whatever the relationship is that we're required to maintain, in this case the negative reciprocal slope. Figure out what that slope has to be. So in this case, in a sense, we're finding that the slope needs to be negative 2/5, so it's perpendicular to this particular lines with that slope. Once we have it, we set it equal to the derivative of our function, and then we solve for whatever value we needed. So again, nothing too crazy, but definitely kind of a different way of asking this question, asking you to make some old relationships come anew, and everything's kind of nice from here. Question number 14 then asks you to do something a little bit differently. This one asks you to explain the origins of the derivative, kind of like the origins of Captain America, but in this case the origins of the derivative. It says to include a description of how we can transform a secant line slope into a tangent line slope using calculus techniques. So I'm not going to write this all out. I'm not as worried and concerned about that part. I think that you should be able to do that though. Instead, I'm just going to kind of draw a picture and talk you through it, since after all that is the one luxury of a video. So remember what the issue was. When we began looking at this problem of the tangent line, our issue was we have the ability to very easily calculate the slope at 2 points, which we call the slope of a secant line because it goes through twice. What we don't have, though, is the ability to calculate the slope of a tangent line. Our issue is, of course, that's just not the way slope's defined. As we all know, slope up to this point has always been based on 2 unique points. We actually calculated it with y sub 2 minus y sub 1 over x sub 2 minus x sub 1, our first ever difference quotient. So that was kind of our issue when we started, was just we don't have that ability. We only know slope as a definition of 2 points. But here was the thing that we did. We were able to set some points on this graph in order to make this possible. And I'm going to use the traditional definition to work my way through just because I think that's more appropriate here. So it just says the derivative. The other one could work just as well. So in particular, we start with our anchor point. And I'm going to say that we're interested in any point x. So this will be on x comma f of x. That's going to be our first point. It's any x value on this curve f of x. From there, we also have a second point. And in order to make sure that that point still is dependent on x, but has some extra little dimension that we can change in order to make this secant line suddenly less and less secanty and more tangenty, we're going to go ahead and define this as not some second value, but x plus h, comma f of x plus h. And the reason we do that is down here, you can kind of imagine, we have an x value where we're starting. Over here, we pick a second x value, and what we do is we add a small little horizontal distance, so that the distance between the two x values is what we're calling h. Some places even call it delta x to emphasize that it's a change in x. Given that, our goal is to make this horizontal distance as small as possible, because a smaller horizontal distance will end up creating a, what's the word I'm looking for? A smaller horizontal distance will create more and more similarity between the actual slope of the secant line and the slope of the tangent line. For instance, right there, this is pretty clearly a secant line. But if I move my second point over to there, you can see that while it's still technically a secant line, it's got a much closer approximation for the slope that we're looking for eventually. So that's what we're trying to do. We're trying to let h get smaller in order to make it so that our secant line becomes more, gets more tangent. And again, I'm using poor words here, but the idea is the same. So in order to do that, in order to kind of finalize that process, what we start with is the reality of where we began. We began with the fact that the slope, based on the fact that it's a secant, is going to be literally equal to the difference quotient. So we called one point 2 with x sub 2 and y sub 2, the other point x sub 1, y sub 1, and we set up the difference quotient like we always have. In our case, that would give us in the numerator f of x plus h, f of x plus h, minus f of x, again drawing from each of those 2 points, all over x plus h minus x. Now, a couple small things here. What you should notice is in that denominator, the x is 0 out, which means that in a sense all we're doing is dividing by h. And that should make sense anyway, because h is the change in x that we have. So in a sense, since delta y over delta x, or change in y over change in x, is describing the slope that we're looking for, in a sense we have that extra little piece. Finally though, at this moment, since we were trying to approximate the slope, or since we were only using a secant line, in a sense this only approximates the actual slope we're looking for, which would be the slope of the tangent line. To make this the exact slope, what we do is we add a limit. We basically want h to get smaller and smaller so the points are closer and closer together. So if we do, and we take the limit as h goes to 0, we will get our actual slope. And this, of course, becomes the slope of the tangent line in the limit. So in a sense, yeah, someone argued this in, I think, first period. Someone said that, well, isn't that still a secant line? Well, technically it is, but because we're going to the limit as h goes to 0, we kind of imagine that we actually reach that point, and then we actually have the tangent line slope. And for sure, at least, it calculates the slope we're looking for. So there is kind of your quick orientation of the origins of the derivative. Hopefully that kind of runs through things and helps you get comfortable with how you can make those things work. Finally, the last question on the first page talks about position, velocity, acceleration connection, kind of the motion application of higher order differentiation. So to start with on 15, it begins by noting that the position of a particle moving along a straight line path is given by s of t equals that function. And it's always a good idea, I think, in my mind, to show you what that means in a picture. So let's close this off really fast, move this down. So I want to go ahead and call this position function s of t, and let's actually put this in here. S of t is 3t cubed minus 10t squared plus 5t plus 4. It says this is for t greater than or equal to 0, but for the moment that doesn't necessarily help us. So let me go ahead and graph a point s of k comma 0. So, and again, I'm going to choose a straight line path to be the x-axis, but again, you could choose a different straight line path in a different direction. I'm just trying to make this as clear as possible. So as of right now, there is the particle that we're talking about. I'm going to go ahead and label it the particle. Okay, so now what you're about to see is what this particle is actually doing. So let me change it so it starts at 0. Let's have it go to 100, and let's have it take really small steps. Okay. Nope, it went really fast. This particle is flying. Let's slow it down. Okay. Nope, it's still going really, really fast. Let's see if we can't slow that down even more. Okay, that is as slow as we can possibly get it. Okay, so there's our particle moving. Notice that, look at that. It kind of goes, watch it one more time. So it looks like the particle goes right, then left, and then starts flying off to the right. And then we can't even keep up to it. So that is the situation we have at hand. It's just moving along some straight line path. Of course, yeah, we think of this as some sort of vertically aligned function, but in a sense all it's doing is telling us its horizontal position while being vertical. So in fact, if I change things around, you could even see it on the side. But that's what we're looking at. We're trying to describe this particle's motion and how fast it's changing. So in here, the first question asks us to find the velocity of the particle. This doesn't really require any understanding of what we just looked at. But for part A, to find the velocity, recall that velocity is equal to the derivative of the position. It's basically the rate of change of the function's position. So in our case, this is a pretty straightforward function to differentiate. In fact, I can do it without writing a whole lot of steps out here. It would be 9t squared minus 20t plus 5. And of course, that gets us the velocity function so that we can find its velocity for any time greater than or equal to 0. But we are specifically interested in the velocity at time t equals 2. So that means that our velocity will be 9 times 2 squared minus 20 times 2 plus 5. As far as ingredients here, we'll get 36 minus 40 plus 5 is equal to, I think, 1. So interestingly enough, it has a velocity of 1 when t equals 2. So good starting spot again. Derivative of velocity, position is velocity. So we use that relationship. For part B, it says there's one time t for which the acceleration of the particle is 42. Find this time. Well, as we did with the previous one, acceleration is part of that position velocity acceleration differential relationship. So the acceleration is equal to, of course, the second derivative of the position function. But for us, it's going to be easiest if we think about it as the derivative of the velocity. It's the rate of change of your velocity, which you should understand for acceleration anyway. When your car starts to speed up, your acceleration is positive because it's moving faster. Its velocity is increasing. So from here, looking at all of our ingredients, v of t was this thing, was 9t squared minus 20t plus 5. So I'm going to take its derivative. In this case, that's going to be 18t minus 20. And now it says that the acceleration of the particle is 42 at one time t. So I'm going to set that equal. Actually, I'll do this with a different color. Sorry. Acceleration is 42. So we're going to set this equal to 42. When we do, we get 18t equals 62. And then we want to find the time. So I'm going to divide by 18. T will be equal to 62 over 18, but if I divide some stuff, particularly by 2, I'll get that t is equal to 31 over 9. So that's the spot for which the velocity of this, or the acceleration of this particle, is literally equal to 42, and whatever the units happen to be. So, with that said, obviously I haven't done the whole review. I've got a couple more pages left to go through, but because of the sake of time and because I want to make sure that I finish something before I go to the reception, that's going to complete my work on this first half. I'll post another video that has the second half of the review, or the rest of the review, later on. So for now, thanks for watching. Hopefully this has been helpful, and have a great day.